All right, good morning. So, as we were doing last time, we're going to continue sort of studying what kind of problems can be modeled as an LP problem. So, if you recall, last time we looked at the short-term investment planning problem. Any questions about that? So, any questions about any of the examples that we've seen so far? All right, so if not, today we're going to continue with a new problem, which is called the product mix problem. Well, we have seen a similar problem before, but this is somewhat different. So, and here is the statement of the problem. So, suppose that milk chocolate is produced with 3 ingredients. So 1 kilogram of chocolate milk contains half a kilogram of milk, um, 0.4 kilograms of cocoa, and 0.1 kilograms of sweetener. Now, each of these ingredients, each of these 3 ingredients needs to be processed before they can be used in the production. Production of chocolate milk. So let's assume that the facility has 2 departments. Has 2 departments that can process these ingredients. And suppose that we have the following information. So here is department number 1. And the figures are given in terms of hours per kilogram. And similarly for department 2. So milk can be processed in department 1 at a rate of 0.4 hours per kilogram. And at department 2, it's 0.6 hours per kilogram. Then the second ingredient, cocoa, can be processed at a rate of 0.3 hours per kilogram and 0.2 in department 2. And finally, sweetener can be processed at a rate of 0.5 hours per kilogram in department 1 and 0.6 hours per kilogram in department 2. So this is similar to the previous examples that we have seen. So in order to process 1 kilogram of milk in department 1, we need actually 0.4 hours. Okay? And similarly, in order to process 1 kilogram of milk in department 2, we need 0.6 hours. Okay? So these are the production requirements, so to speak. So we assume that the available number of hours in each department is 150 per week. So in each department we can use this many hours basically. And the question is the following. So formulate an LP problem that maximizes the total number of kilograms of milk chocolate produced in a week. So let me quickly go over the problem again. So suppose that we produce chocolate milk, and chocolate milk has 3 ingredients. which are milk, cocoa, and sweetener. Each of these three ingredients actually needs to be processed before they can be used in the production. And we have two departments that can process these ingredients. So we're given the information in terms of production requirements. So as I said, to process 1 kilogram of milk in department 1, we need 0.4 hours. Whereas in department 2, we need 0.6 hours. And then we're also given that in each department, we can use at most 150 hours per week. Okay? Now, subject to these sort of restrictions, we would like to formulate an Alper problem which would maximize the total number of kilograms we can produce, total number of kilograms of chocolate milk we can produce in a milk chocolate that we can produce in a week. Okay? So first of all, is the problem clear? So this is again a sort of kind of production planning problem. Okay? And what we want to do is we would like to figure out the sort of largest number of kilograms of chocolate milk we can produce in a week. Okay? So let's try to figure out our decision variables. So let's actually think about the following. So what are the factors we can control in this problem? So what are our decision variables? Sorry? Which department are we going to use for which ingredient, basically, right? So in other words, how much of the first ingredient are we going to process in department 1, and how much of the first ingredient are we processing in department 2, and so on and so forth. Okay? So how can we sort of define our decision variables? What would be a natural way of doing it? So we could use Xij, right? Basically, because I refers to the ingredients, so I can be milk or cocoa or sweetener, and J refers to the department, so J can be equal to 1 or 2. So let's define our decision variables in that way. So Xij is going to be the number of kilograms of ingredient I processed in department J. So remember, whenever we define Xij, we need to figure out the sort of possible values for the indices. So what are the possible values for index I? So I can be 1, and 1 stands for milk. I can be 2, which stands for cocoa, and it can be 3, which stands for sweetener. And J can be 1 or 2 because we have two departments. So basically, X11 is the number of kilograms of milk that will be processed in department 1. Okay? All right, so anything else? Do we need any other variables? Well, remember, our goal is to maximize total number of kilograms of chocolate milk that we're going to produce, right? Okay? And that, of course, depends on how much ingredient we're going to process in each department. Okay? So what I'm going to do is I'm going to define another decision variable, which I'm going to call y. And y stands for number of kilograms of milk chocolate produced in a week. Now, it's not too hard to see that there is a relationship between y and Xij's, right? So the amount of production obviously depends on how much ingredient I'm going to process. Okay? And these are the only variables actually we need for this problem. So now I'm going to ask you the following question. So what is the correct relationship between y and Xij's? So if I know the values of Xij's, can I figure out the value of y? And if so, how can I do that? Well, there's one thing you need to be careful about, because essentially, if I go back to the problem, so to produce 1 kilogram of chocolate milk, I have to have this much milk, this much cocoa, and this much sweetener. So which means that essentially, when I process the ingredients, I should pay attention to these proportions. Okay? So if I want to produce exactly 1 kilogram of milk, then 1 kilogram of milk chocolate, sorry, I need to process exactly this much of milk, exactly this much of cocoa, and exactly this much of sweetener. Okay? So what does that mean? Well, essentially, you know, in this particle production planning problem, you have to sort of pay attention to proportions of the ingredients, okay, that you're going to process. So if you come up with a production plan in which, for example, you know, you process, you know, tons of milk and you process tons of cocoa, but you don't process any sweetener, then you cannot produce anything at all. Is that clear? Let me repeat that again. So suppose that you have 100 kilograms of milk, 100 kilograms of cocoa, but no sweetener. Then how much production are you going to have? 0, basically, right? So as a result, you know, when you process the ingredients, you have to be careful and you have to pay attention to these proportions of the ingredients. Okay? So now my question is the following. So if I tell you that, for example, I have, let's say, 2 kilograms of milk, 2 kilograms of cocoa, and 2 kilograms of sweetener available, how much chocolate milk can I produce with those ingredients? So this is not too hard, right? So if you have 2 kilograms of each of them, what's the largest what's the largest production you can have in terms of chocolate milk? So it's going to be, well, milk will determine, basically, how much you can produce. So all I'm going to do is I'm going to divide 2 by 0.5, and I'm going to divide 2 by 0.4, and I'm going to divide 2 by 0.1. That will give me the largest amount I can produce, provided that the other ingredients are sufficient, basically. And then I'm going to take the minimum of those 3. Okay? So in other words, essentially, we can formalize it. Y is given by the following. So it's going to be the minimum of, so x11 plus x12. So what is x11 plus x12? So it's the total amount of milk I'm going to process. Right? Department 1 plus department 2. Okay? So total number of kilograms of milk I'm going to process. And I'm going to divide it by 0.5. Then I'm going to look at the second ingredient. So x21 plus x202. I'm going to divide it by this time 0.4. So this is the total amount of cocoa that I'm going to process. And I'm going to divide it by 0.4 to figure out the largest amount of chocolate milk I can produce. Okay? And by the same reasoning, I have x31 plus x32. And I'm going to divide it by 0.1. So I have 3 ratios. Okay, just like I did in the previous example. And whichever is smallest will determine my production level. Does everyone see that? So essentially in my example, you know, I said this is equal to 2, this is equal to 2, and this one is equal to 2. So if you compute these ratios, you have 4 here, you have 5 here, and you have 20 here, basically. Smallest one is this one, so this determines your production level. Okay? So in other words, for example, if you come up with this production schedule in which, for example, this is equal to 0, okay? So which means that you don't process any sweetener at all, then your production amount will be 0 as well. Does everyone see that? So is it clear why am I dividing by these numbers? Well, as I said, I mean, the reason comes from these proportions. So basically, to produce 1 kilogram of milk chocolate, I need 0.5 kilograms of milk, 0.4 kilograms of cocoa, and 0.1 kilograms of sweetener. So as a result, these ratios will tell me, for example, if I just look at this ratio, this is the largest amount of chocolate milk I can produce, provided that I have sufficient number of available other ingredients. Okay? So by the same reasoning, this is the largest amount of chocolate milk I can produce, provided that I have enough milk and enough sweetener. And similarly, this is the largest amount of chocolate milk I can produce, provided that I have enough milk and enough cocoa, basically. Okay? And whichever is smallest rather, will determine how much production I can have. Does everybody see that? Any questions about this? All right, so therefore, if I know the values of xij's, I can compute the value of y. Okay? And remember, my goal is to maximize the value of y, because y corresponds to production level. Okay? And my goal is to maximize my production level. So as a result, I want to maximize y. And the relationship of y with the other variables are given in this equation, basically. Okay? So what I can do is the following. I can start by maximize y, right, which is my objective function. Now, when I write down the constraints, you know, I'm going to say y is equal to the minimum of these expressions. Okay? So I can put this as a constraint. But there's one problem, right? The problem is that this does not look like an LP constraint. Why not? Because in an LP constraint, remember we have a variable times a constant plus a variable times a constant, so on and so forth, either less than or equal to or greater than equal to some other constant. And this constraint is not in that form. Does everybody see that? So I cannot actually put it as a constraint in my problem. Okay? And if I do, this would not be an LP problem. Okay? So as a result, I have to do something about this. So the problem is that, so this is not an LP constraint. Well, so what are we going to do? Well, they asked us to model the problem as an LP problem. But unfortunately, this is not an LP constraint, so I have to do something about this. Okay? So essentially what I need to do is the following. I need to take this constraint, and I need to express it as equivalent LP constraints. Okay? So I need to come up with a sort of one or more constraints so that the constraints actually would be equivalent to this expression. Okay? They would be in the LP constraint form, and they would be equivalent to this formulation right here, this equation right here. Okay? Before I move on, is the problem clear? So does everybody see what the problem is? So as I mentioned, this is not a constraint that can appear in an LP problem. Okay? So as a result, I cannot simply say that y is equal to this in my LP problem. If I do that, this is not going to be an LP problem. Okay? If you think about this a little bit, so this does not look like a typical LP constraint. Okay? In an LP constraint, we can never have such operations like minimum of these ratios. Okay? So the question is, what are we going to do about this? Well, let me start by constructing our model. So my goal is to maximize y. Y corresponds to production level, so that's going to be objective function. And that's a perfect defined objective function, right, for an LP problem. That's okay, right? So it's an LP objective function, okay. So I'm going to come back to that expression later on, but let's sort of figure out, do we have any other constraints in this problem? Well, for example, we have the availability constraints. So let's try to figure them out. So the available number of hours in each department is 150 per week. How can I formulate as a constraint? Well, I'm going to look at department 1. I'm going to compute total number of hours I'm going to use. Then I need to make sure that those hours cannot exceed 150, right? So how can I write this as a constraint? Well, if I process x11 kilograms of milk in department 1, I'm going to use 0.4 times x11 hours, right? Similarly, I'm going to use 0.3 times x21 and 0.5 times x31. And if I add them up, it's going to give me a total number of hours I'm going to use in department 1, right? So let's write it down. So 0.4 times x11 plus 0.3 times x21 plus 0.5 times x31. So once again, this is total number of hours I'm going to use in department 1. And I want to make sure that this is less than or equal to 150. Okay? I'll just do the same thing for department 2. So 0.6 times x12 this time. 0.2 times x22. Plus 0.6 times x32. And this cannot be larger than 150. So the first constraint is for department 1, and the second one is for department 2. So we have two availability requirements. So once again, it's a good idea to note that in the first constraint, the second index is the same, right? So the second index corresponds to department 1, and I'm only changing the first indices. And in the second one, the second index again is fixed, but this time it's fixed at 2, and the other indices are changing. Okay, so I'm actually summing over the first indices in other words. Okay? All right, so what else do we need? Well, we have to somehow figure out writing this as an LP constraint, right? Okay? So once again, the problem is that if I take this equation as this, and if I plug in here, this would not be an LP problem. Okay? So as a result, I have to do something about this. And let me try to explain by a picture of what we're going to do. So think of this as a real line. Okay? So all the real numbers are located on this real line. So it goes to plus infinity, minus infinity. So let's say for particular values of x11, x12, x21, x22, x31, x32, what I'm going to do is I'm going to compute these numbers, okay? And I'm going to plot them on the real line. Okay, so for example, maybe the first one corresponds to this number right here. Okay, the second one maybe corresponds to this one right here, and the third one is maybe this one right here. Okay, so these are three different numbers potentially. Okay, and what I would like to do is I would like to set y to be equal to the minimum of these three numbers. Okay, and obviously in this case the smallest one would be this one, so I want y to be equal to this one. Okay. Now I'm going to make the following observation. So if y is equal to the minimum of those three numbers, okay, then y should be less than or equal to each of these three numbers. Let me repeat that again. So if y is equal to the smallest of these three numbers, then y cannot be larger than the smallest of these three numbers. Okay? So which means that if I have three ratios or three numbers here, let's say the first number, second number, and third number, then my y variable cannot be larger than any one of these numbers. Okay? So what I'm going to do is I'm going to take this relation, okay? And first of all, I'm going to write in the following way. So I'm going to say that y should be less than or equal to the first ratio, x11 plus x12 divided by 0.5. Then y is less than or equal to the second ratio, which is x21 plus x22 divided by 0.4. And y is less than or equal to x31 plus x32 divided by 0.1. Now let me ask you a question. So are these valid LP constraints? Not yet, but they can be put into, well, from LP constraints, right? So how am I going to do that? Well, so basically I can put everything on the left-hand side. And if I do that, I can write it in this way. Okay? I'll just do the same thing here. And then I'll just do the same thing over here. So now, rather than having only one sort of relation, I have three constraints basically, right? But the difference is that these are now valid LP constraints. Okay? Now there's one thing you have to be careful about. These constraints, these relations, these three relationships, inequalities, are not the same as that relationship, right? Why not? Because, for example, if I look at only these constraints, then y can be equal to, for example, this number as well. Right? If I want y to be less than or equal to each of these three numbers, then I can set my y somewhere over here, in which case y would not be the same as the minimum one. Does everybody see that? So essentially, once again, this relation here, so y, the fact that y should be equal to the smallest of these three numbers, is not actually the same as these relations. Okay? In general. Because as I said, you know, if you just look at these constraints, you can set your y to be something even smaller than the smallest number. And you will still satisfy these constraints. Does everybody see that? So in other words, these three constraints do not necessarily guarantee that y should be exactly equal to the minimum. Okay? However, if I look at my objective function is trying to increase y as much as possible. Okay? So what does that mean? Well, my objective function would never actually choose a value of y such as this one. Okay? It will always try to push y as much to the right as possible. Okay? And if it does that, then the best value of y indeed would be equal to the smallest number here. Okay? So as a result, by combining these three constraints with the objective function, we ensure that y is precisely equal to the smallest of these three numbers. Does everybody see that? So this is really important because essentially what we did was the following. So this constraint, the fact that y is equal to smallest of these three numbers, is not a linear constraint actually. Okay? However, despite the fact that this is not a linear constraint, we can still express it as linear constraints. Of course, I mean, we need to write more than one constraint, basically. But still, I mean, we can formulate this problem as an LP problem, which is really nice. Okay? So as a result, there are some examples, such as this one, in which the relationship is not linear. Okay? However, they can be turned into linear relations using these simple tricks. Okay? Let me repeat this part once again because it's important. So essentially, what I'm trying to do is, you know, these are my three ratios. the three ratios coming from those expressions. Okay? And what I would like to do is I would like to set y to be the smallest of these three ratios. So I want y to be exactly equal to this one. Okay? So first of all, I'm making the simple observation that if y is equal to the smallest one of these three ratios, then y should be less than or equal to each one of these ratios. So based on that, I'm actually writing these constraints. However, those constraints alone only tell me that, for example, y can take any value up to this point. Okay? So in particular, for example, my constraints can pick y to be equal to this number right here as well. Okay? Of course, in that case, y would not necessarily be equal to the minimum of these numbers, right? Y would always be less than or equal to the minimum, but this does not guarantee that it's going to be equal. Okay? However, what I'm saying is the following. If I look at my objective function, the objective function is trying to increase the value of y as much as possible. Okay? So as a result, rather than picking this value for y, my objective function will try to push y as much to the right as possible, in which case y will necessarily coincide with the smallest number. Okay? So as a result, in my optimal solution, y will always be equal to the smallest of these numbers. Is that clear? So any questions? This is important. I just want to make sure that everybody understands this. So does everybody see how this works? Or why this works? Because if the answer is yes, I'm going to move on to a harder problem. Okay? So any questions about this again? All right, so anything else do we need in this problem? So what's the one thing we should never forget? Non-negativity, exactly. So xij should be non-negative for all values of I and j. What else? Y should also be non-negative. So as a result, if I solve this problem, then I'm going to be able to solve the original production planning problem, okay? So once again, I mean, there's an important message here, and the message is the following. Despite the fact that in some problems you may sort of see constraints which do not look like LP constraints, you can always convert them into LP constraints. Okay? And this is one such example, basically. Okay? So in this example, we were able to write down this constraint which does not look like an LP constraint as LP constraints. Okay? So that's important. Okay? All right. So unless there are any questions, I'm going to move on then. So now we're going to look at a slightly harder problem. Example 10. So suppose that you estimate that there is a linear relationship linear relationship between the stock price of a beverage company such as Coca-Cola or whatever, so and the number of beverages sold. And we're going to assume that these numbers are given in thousands, sold in a day. So suppose that you invest your money in the stock market and you invest your money in one of the beverage companies, and then you track their performance and you look at how many beverages they sell every day, and you also check the stock price, and you assume that there's a relationship. Okay, so if there's more demand for their products, then the stock price will go up, and if there's not enough demand, then the stock price will go down. And suppose that we're given the following information. So this is day, stock price, and then number of beverages sold. So in day 1, the stock price is 2, and number of beverages sold is 10. 10,000 basically, okay? In day 2, the stock price is 3, and the number of beverages sold is 12. In day 3, the stock price is 2, and the number of beverages sold is 8. In day 4, the stock price is 3, and the number of beverages sold is 11. And in day 5, the stock price is 4, and number of beverages sold is 14. Now, if you look at this information, okay, so suppose that this is the information from the last week, it's not too hard to see that there's not a perfect relationship actually, right? Because, for example, when the stock price is 2, the number of beverages actually should be the same, but they're not the same, okay? Well, they're not too different, but they're not the same. So which means that there's not a perfect relation, but there is some sort of a relation, basically. For example, number of beverages sold goes up to 14, and stock price goes up to 4. Number of beverages goes down to 8, and stock price goes to 2. So there is some relationship. There's not a perfect linear relationship, but there is a relationship. So what you want to do is, you want to estimate the best possible relationship between these two, okay? So essentially, you predict the relationship as SI equals A times NI plus B, where SI is the stock price, and NI is the number of beverages sold, on day I. So I can be 1, 2, 3, or 4. So there's one thing I need to emphasize here. So basically, SI represents the stock price. So this is S1, S2, S3, S4, and S5. And NI represents the number of beverages sold. So this is N1, N2, N3, N4, and N5. Okay? What are the unknowns? Well, the unknowns are the coefficients A and B. Okay? So you would like to predict those coefficients. Okay? So remember, if there's such a relationship, then this is a linear relationship, right? The stock price depends linearly on the number of beverages sold. Okay? So what we don't know for this problem is the true values of A and B, of course. Okay? So what we want to do is we want to figure out the best possible values for A and B. And what do we mean by the best possible? Well, so here's our performance sort of measure. So for a given choice of A and B, as I said earlier, there's not a perfect relationship between the stock price and the beverages sold, right? Why not? Because, as I said, there are 2 days for which the stock price is 2, but number of beverages sold is different, actually, on these days. So this is not a perfectly true relationship, basically. Because if the relationship were true, then for every choice of number of beverages sold, we would always have the same stock price. Okay? However, in real life, that's not the case. So for a given choice of A and B, your estimation error on day I is given by the following. So SI is the actual stock price minus A and I plus B is the predicted stock price by your model. So what we do is we look at the difference and we take the absolute value. So we can deviate in either direction. Okay, so as a result, we just take the absolute value. And I will be equal to 1 through 5. So what does this mean? So for example, you assume that A is equal to 1 and B is equal to 0, just as an example. Okay? And for A equals 1 and B equals 0, so your relationship becomes SI equals NI. Right? So what do? Well, you look at this model and you try to fit your model to the actual data. Okay? So for example, for day 1, N1 is equal to 10. And if the relationship were true, if SI were equal to NI, then S1 would be equal to 10 as well. Okay? But the true value of S1 is 2. So what I do is I look at the difference between 2 and 10, which is 8, minus 8. And then I take the absolute value. Okay? And I'm going to call it my estimation error, basically. Okay? For that day. So essentially, think of this as the true value. and think of this as the estimated value. And what I'm doing is I'm looking at how much different they are from one another, basically. Is that clear? Is this clear? So I'm looking at the difference between the true value, true stock price, and the predicted stock price, basically. Okay? Predicted by me, of course. I'm predicting that the stock price obeys this relationship. So for each value of A and B, there's going to be a certain estimated value, and that might be the same as true value, or it might be different. Okay? So what I'm going to do is I'm going to try to look at this difference, and I'll take the absolute value because my estimate can be higher or lower. Okay? So my estimate can go either way, so as a result, I'm just taking the absolute value. So essentially, I'm looking at how much I deviate from the true stock price. Does everybody see that? All right. So our goal is the following. Choose the unknown coefficients, A and B, so that the largest estimation error on any of the 5 days will be as small as possible. So let's try to understand the objective again. So A and B are my unknown coefficients that I would like to determine. So for every choice of A and B, there's going to be a different model, right? A different prediction, basically. Now, what I'm going to do is the following. If you give me a specific value of A and B, let's say 10 and 1, just as an example. So what I'm going to do is I'm going to compute my estimation error on each of the 5 days, okay, using that formula. And whichever is largest among those estimation errors, I'm going to actually pick that one, okay? I'm going to call it as my estimation error. So my estimation error would be the largest estimation error, okay? So what am I trying to do? I'm trying to pick A and B in such a way that my largest estimation error will be as small as possible. Okay, so I'm trying to sort of do the best I can on the worst possible day. Okay, so it's kind of a pessimistic approach in some sense. So this is called a min-max problem. I'm trying to minimize the maximum of the largest errors, maximum of the estimation errors. Sorry. Okay, so if this is still not quite concrete, here's the picture. So think of this as the number of beverages sold, and think of this as my stock prices. Okay? So essentially what we're doing is the following. So I have the values of 8, 10, 11, 12, and 14 here. And then, for example, if I look at day 3, the stock price is 2. So this is a value of 2. And then if I look at day 1, the stock price is still 2. Okay. What else? Then if I look at day 4, stock price is 3. So I'm going to go ahead and plot this one. Okay. And then on day 2, stock price is still 3. And then on day 5, the stock price is 4. So this is my data, basically, right? If I plot my data, this is the real data. So what am I trying to do? I'm trying to estimate that there's a linear relationship. So, for example, such as this one. So this is going to be my estimate. Okay. Now, what's my estimation error? Well, for example, if I look at this red line corresponds to a specific choice of A and B. Okay? If I look at this red line, for example, if the number of beverages sold is 8, then my model is predicting the stock price as this one. Okay? Whereas the true stock price is this one right here. So what's my estimation error? Well, the estimation error is precisely this difference right here. Okay? For example, on this day, the estimation error is this one. Then on this day, it's this one right here. On this day, it's this one. And finally, on this day, it's going to be this one right here. So essentially, what I'm doing is the following. for each of the 5 days, I'm computing these estimation errors. Note that in some cases, I'm actually overestimating. In some cases, I'm underestimating, okay, the stock price. And then what I'm doing is I'm looking at the largest of these small segments. Okay, for example, in this case, I guess this is going to be the largest. Then for this particular model, my estimation error would be equal to this one right here. Okay? The largest among those deviations would be my estimation error. And what I want to do is I want to pick my red line in such a way that the largest estimation error will be as small as possible. Okay? So in other words, this basically means that I'm trying to figure out the best possible linear relationship among my stock prices and number of beverages sold. Is the problem clear now? Okay. So how are we going to model this problem? Well, first of all, let's start with the decision variables. Note that if I change A and B, then my line will change basically, right? So if I change A, for instance, then the slope of the line will change. And if I change B, then my line will shift up and down. Okay? So there are two factors that affect my decision. A denotes the slope of this line, and B denotes the shift of this line, basically, right? So how the line shifts. So what are decision variables? So what am I deciding here? What can I control? Well, I can control how I'm going to pick my red line, basically, right? Okay. And that, in turn, is controlled by A and B. Okay? I have no control over stock prices. I have no control over number of beverages. The only control I have is over A and B. Okay? So as a result, A and B are the unknown coefficients. Okay, so now let's figure out how we compute our estimation error again. So how do we compute that? Well, I start with the first day. Okay. So for a particular value of A and B, what's the estimation error on first day? So I'm going to use that formula. Okay. So for I is equal to 1, S1 is equal to 2. Right? And N1 is equal to 10. So I'm going to plug in S1 equals 2 and N1 equals 10 into that expression. And that's going to be my estimation error on day 1. Okay? So let's try to sort of figure that out. Let me use the other board. All right, so essentially, first of all, I'm going to compute my estimation error on day 1. So the true stock price is 2, minus the estimated one is given by A times 10 plus B, so 10A plus B. So this is going to be my estimation error on day 1, right, for a certain choice of A and B. Okay. Then I'm going to look at the estimation error on day 2. The true stock price is 3, and the estimated stock price will be 12 times A plus B. So this is going to be the estimation error on day 2. So these actually correspond to those little red segments, okay, deviation from the red line. Okay. What about day number 3? So the true stock price is 2. Okay. What's the estimated stock price? So N3 is equal to 8. So I'm going to plug in 8 into this formula. So 8 times A plus B, right? So I'm going to have 8A plus B. Then on day 4, the true price is 3. What's the estimated price? 11A plus B. Good. And finally, on day 5, the true price is 4. And what's the estimated price? So it's going to be 14A plus B. Okay? Now, these are my estimation errors on day 1, day 2, day 3, day 4, and day 5. Okay? So what am I going to do? I'm going to take the largest of these errors. Okay? So I'm going to actually take the maximum of these errors. And the maximum of these errors will give me my estimation error for this choice of A and B. Okay? then I want to pick my A and B in such a way that this value is as small as possible. Okay, so I want to make sure that this one is as small as possible. So what I'm going to do is, I'm going to call it y. Okay, just like we did on the previous example. So therefore, what I'm going to do is, I'm going to try to minimize y. Okay, by minimizing y, I'm actually minimizing my largest estimation error. Okay. Well, there's one problem, just like the one we had actually in the previous problem. I cannot simply put this as a constraint in my problem. Okay? Well, I can, but it's not going to be an LP problem. So I have to do something about this. So remember last time we had y equals the minimum of some numbers. So here we have y equals the maximum of some numbers. So how can we actually sort of deal with this? Exactly. If y is the largest one of these 5 numbers, then y should be at least as large as any one of these numbers, basically, right? So I'm going to write it that way. So y should be at least as large as 2 minus 10a plus b. Then y should be at least as large as 3 minus 12a plus b. Then y should be at least as large as 2 minus 8a plus b. Then y should be at least as large as 3 minus 11a plus b. And finally, y should be at least as large as 4 minus 14a plus b. Well, once again, by the same reasoning, these 5 constraints are not essentially the same as this one, are not necessarily the same as this one. Okay? So these constraints simply tell me that y should be at least as large as the largest one of these numbers. Okay? However, again, if I look at my objective function, since the objective function is trying to minimize y, okay, then y will necessarily be equal to the maximum of these numbers. Okay? So in the previous problem, we had the other way around. So we're trying to maximize y. So that would make sure that y would be equal to the minimum one. So here we're minimizing y, and this would make sure that y will be equal to the largest of these numbers. Okay? By the same reasoning. Does everyone see that? All right. Well, there's one problem, though. Are these LP constraints? No, they're not LP constraints, unfortunately, right? So why not? Because we cannot have absolute value in an LP problem. Okay? So still not an LP problem. But we made some progress, right? So at least now it looks a bit simpler than before. So the question is the following. How can I turn this, or can I turn this into an LP problem? Well, let me ask you a simpler question. So, for example, in calculus, you have seen inequalities such as x is less than or equal to 5. Right? Absolute value of x is less than or equal to 5. So how can I write this in a different way? So x should be between minus 5 and plus 5, right? Okay? Well, then I can write this as x is less than or equal to 5, and x is greater than or equal to minus 5. Well, this is not an LP constraint, but these are LP constraints. Okay? So I'll just play the same game, right? I'll just do the same thing. So I'm going to minimize y, subject to. All right, so how can I deal with the first one? 2 minus 10a plus b should be less than or equal to y. Okay? So try to think of that example. Then what else should I need to write? So by the same reasoning, so this should be greater than or equal to minus y, right? Okay? So try to think of this as my x. Okay? So x is less than or equal to y, x is greater than or equal to minus y, just like we had over there. Then I'll just play the same game for other ones. So 3 minus 12a plus b is less than or equal to y, and 3 minus 12a plus b is greater than or equal to minus y. Then I'm going to look at the third one. So 2 minus 8a plus b is less than or equal to y, and then 2 minus 8a plus b is greater than or equal to minus y. then for the fourth one, I have 3 minus 11a plus b is less than or equal to y, and 3 minus 11a plus b is greater than or equal to minus y. And finally, 4 minus 14a plus b is less than or equal to y, and 4 minus 14a plus b is greater than or equal to minus y. Do I have any restrictions on A and B? Any other restrictions? Well, not necessarily, right? So A and B, well, okay. If there's a true relationship, then A and B should be non-negative, obviously. But since we're working on past data, the best value of A and B can be negative as well, okay? So, which means that essentially, if you get something like that, then your predicted relationship is not quite correct in some sense, okay? Because the stock price cannot be negative. So in general, we don't have any restrictions on A and B. Do you have any restrictions on Y? Well, it's not too hard to see that if Y satisfies these relationships, then Y is automatically non-negative, right? So there's no need for additional constraints as well. Y will always be non-negative if I solve this problem, so I don't need that constraint. So basically, if I solve this problem, then I'm going to solve the original problem as well. Okay? So the solution of this problem will give me the best choice of A and B so that the largest estimation error would be as small as possible. Okay? So what's the bottom line? The bottom line is the following, basically. In this lecture, the two problems that we have seen are problems that look like they cannot be formulated as an LP problem, okay? Because in both of them, we have like absolute values and means and max and so on and so forth. But it turns out that for certain problems, such as this one and the last one, you can still actually turn them into LP constraints, okay? So which actually gives you an idea of about the power of LP modeling in some sense, okay? So despite the fact that the problem may not look like an LP problem, you can still convert it into an LP problem. Okay? So I'll see you next week.